Hello, I'm David Green. I'm a geologist with Mineral Resources Tasmania, a spectral geologist mainly, and I'm going to take you through hyperspectral logging, use of infrared spectroscopy to identify minerals in mainly drill core, and how that can be used for a range of purposes, many of which can be applied to geometallurgy. Okay, on with the show. High logging, so it's hardware and software for objective scanning of in a voluminous way of all drilled materials like diamond drill core, chips, and we get outputs as logs, typically digital, and can be they support and augment logging by geologists. The handheld analyzers are typically used in the field. The ASD Terraspec Halo is probably the most common one, but or Express there as well, and the Agilent offer thermal infrared capture as well as normal shortwave infrared. The drill core imaging systems offer some very detailed analysis of usually smaller amounts of material. One advantage they have is that each pixel is very small, so you only see one mineral in it. And whereas a handheld scanner or a drill core scanner will normally see a larger area of material, so you have to deal with the unmixing of the spectrum to end-member minerals. So core scan, TerraCore dominate in this area, Spectrum in Finland. So opportunities for imaging for shortwave infrared spectroscopy at a range of scales, and what we focus on at MRT is the high logger, which is a profile scanner for drill core. So uses reflectance spectroscopy. There are three spectrometers dealing with the visible and near infrared, the shortwave infrared, and the thermal infrared. And basically a core table with drill core on it moves around robotically underneath an array of instruments, so that we're sampling about 125 samples per meter. Each sample is about 10 by 18 millimeters. And it also includes high resolution RGB imaging, and it's married to the spectral geologist software. High logging can be set up usually in either containers, top left, top right, or standalone in a core library, typically in the middle. And it can be mobile. And just showing at the bottom right, there's a new kid on the blocks of a cut down version of a high logger like instrument, which could be set up in any core library for pretty quick analysis. Hyperspectral scanning, really, we're looking at things in infrared light. So two minerals that may look the same in RGB, the mineral may look, both of them are going to be green. Well, in infrared light, they look completely different. And so that's what we're using. Okay, we're using it in the infrared light system that's just beyond the infrared, just beyond the visible, so just out here, right out to the thermal infrared, far from what the eye can see. And the high logger sees in the visible and near infrared with a whole lot of channels in that area, a lot more channels in the shortwave infrared where things get most interesting mineralogically, and the thermal infrared out here at the thermal wavelengths, with a gap between that and the shortwave infrared here, the middle infrared, which will be filled by the high logger 3 coming out in late 2021. What happens when the light is reflected is detailed in this slide, where we have a source of infrared light, and the surface, the light gets onto or into the target, and then what gets reflected we detect out here. So in the visible and shortwave infrared, light goes into the sample, it's scattered within the sample, wanders around, it gets to see all the minerals that are in there, interact with those minerals, and then is detected. And so most of the light is actually reflected in a way. It's scattered, it goes in and it comes out. And the general spectrum is has a reflectance of 100%, but it's impinged by absorptions due to interaction with minerals, where some of the light is absorbed by the minerals. In the thermal infrared, most of the light is actually absorbed at the surface by internal reflections. So it goes just into the surface of the sample and stays there. It just heats up the material. But at certain wavelengths, it does get reflected a bit like a mirror, and those reflections are characteristic of the mineralogy. Okay? So what causes these absorptions? It's interaction with molecular bonds, where the light is of a wavelength that is an energy which resonates with a molecular bond, then we will get in the shortwave infrared absorption. The light will be absorbed there, and that bond will be energized, so the light will be absorbed by the mineral at that wavelength. And here, in this case, for an asymmetric stretch, we can see that the light gets absorbed at a certain wavelength that resonates with the energy of this bond. The wavelengths that these processes occur at are typically out in the thermal and the middle infrared, and what we have is overtones of these, and combinations of them is what we see in the shortwave infrared. Okay, so this is the first stretching overtone region. So it's a stretching bond, and it's an overtone of that. So that's why it's got the two, and we can see an absorption related with that. Okay, and then there's a third overtone up here, and there are combinations of bendings and stretchings which create absorption features which are actually quite complicated in detail. This is how complicated they can be. So one feature here, which is all a feature associated with the AlOH molecular bond, has detail which is related to combinations of various components of bendings and stretchings. Okay? Now, we don't need to deal with those details in the hyperspectral geology we do. It offers wonderful opportunity for characterizing things in detail, but we don't have the spectral resolution to see that. But we can see that it's an AlOH bond, so typical of a white mica, will cause an absorption of this shape and wavelength here. Okay, the other type of main type of absorption process which can occur is down in the visible area, so visible out to this area here and very near infrared down here, where absorptions are due to interaction of the light directly with atomic orbitals of electrons, and by charge transfer and crystal field processes, which are technical ways of saying we're looking at the electrons directly here. And these features tend to be really broad, not sharp, so they're useful, but they're not. They don't characterize minerals in a very particular way because the features are just not sharp enough. Nevertheless, they're useful mainly for things which have lots of iron in them. It's a typical place we'd see these, so hematite, goethite, good for characterizing those sorts of things. Now, there's one other type of absorption, and these are rare earth elements. The atoms actually have their own spectral fingerprint. So we're directly seeing here rare earth elements, be they in allanite or whatever. So if there's plenty of that around, you can sometimes see these very sharp absorptions down near the visible area of rare earth elements. It's a specialized area. Okay, the high logger sees then these crystal field or charge transfer effects down in the visible near infrared. It sees scattering and absorption in the shortwave infrared, and it sees reflectance features in the thermal infrared. And the minerals that we see in these areas are somewhat complementary. So the high logging systems, as I said earlier, it aims to be objective and it needs to be consistent. It gets lots and lots of samples, so we're talking thousands and thousands of samples, tens of thousands of samples in a drill hole, which gives us increased confidence. We get reduced handling because the core is scanned in the original trays dry. It allows geologists to do other things. We can see different things in spectral geology. We can see spatial trends, we can see minerals which are not easily identified visibly. And the whole system's great for a long-term view. So the same data set can be used in greenfields exploration right through to to brownfields deposit characterization, geometallurgy, obviously, and the earlier all this can happen, the better. The high logging, it targets the mineralogical composition, not elements. So the things, if you want geochemical methods, that's where you go to the XRF. The samples have to be dry. It is fast to scan. It's something like, it would take about 5 minutes to do one tray. You can do sort of like 200 to 500 meters in a day. And this is with a high logger. I think you can do a lot quicker with a handheld device if you're sampling every 1 meter or so, but you're getting 1/100th the number of samples as you can with the high logger. High logging provides a very dense data set. You can get really good statistics because of all this redundancy of oversampling. So you can be sure of what you get. You get relative proportions of minerals, not modal abundances, but you can calibrate against external standards to make estimates of real relative proportions. And high logging can see, if you like, minerals which are hard to see otherwise. So clays are like that, or the composition of the clays. And there are compositions of minerals which it can, if you like, see as well. So that's great. So we're using hyperspectral geology to measure things which are not just what we see with our eyes. And of course, it does the same thing day in, day out, so it's very objective. What can it see in the visible near infrared and the shortwave infrared? Hematite and goethite iron oxide minerals can be seen. All the white micas, clays, kaolinite, gibbsite, all those sorts of things are easy to see. These are all AlOH group minerals. Alunites, gypsum. We can see silica indirectly just by seeing the fluid inclusions in quartz where there are no other features. So it's not a great way of looking at quartz, but we can see it. Alunite, some of the saponitic minerals, chlorites, serpentinites, amphiboles, carbonates, and a few epidotes, perenites, some things like that. Topaz to a degree, topaz for sure. Some zeolites, and as we discussed, rare earth minerals. And massive sulfides, but only when there's plenty of them, like we're talking 15%. In the thermal infrared, we see, we see pretty much everything else, like potassium feldspars, plagioclase feldspars, quartz, pyroxenes, olivines, garnets, zeolites, amphiboles again, the metamorphic minerals, tourmalines, carbonates, and also all the minerals we saw before. But these minerals are better delineated in the shortwave infrared than the thermal, which is more tuned to all the other minerals, more silicates. The spectral geologist is software that's grown up with high logging and is used with it. You don't have to use that. You can use NV or other products, but TSG offers you a lot of tools for analysis of hyperspectral data. I'll go through that quickly, the sorts of things that it's used. In the summary screen, we can see here at the top the summary of the going down hole depth here, showing the shortwave infrared delineated mineralogy. So the mineralogy has been determined by an automatic algorithm within the spectral geologist called the spectral analyst. And here we can see it's yellow is white mica and green is chlorite, and the relative proportions of the two vary as we go down the drill hole. So 50-50 here, and more dominated by white mica here. Carbonate in blue, and the grey is aspectral material, probably a shale. In the thermal infrared, we see really that the rock is mainly made up of quartz and the brown plagioclase, and the white mica really is only 20% of the rock. But because the shortwave infrared does not see the quartz or plagioclase, it's transparent to the shortwave infrared light. It just sees the white mica and chlorite that's sitting in there. So it's quite sensitive to small amounts of the chlorite and white mica. You can see the chlorite barely features down in the thermal infrared at all, but it's picked up really well in the shortwave infrared. So the shortwave infrared goes into the material, samples a volume of material within otherwise transparent shortwave infrared materials like quartz and plagioclase, but the thermal infrared just sees the surface of the material, and it's a truer reflection of the actual proportions of the mineralogy. We can see each spectrum, or 4mm or 8mm sample, in detail. Here we can see the unmixing result for this sample here, chlorite plus epidote, and in the thermal infrared it's quartz plus garnet. So this screen is for looking at things in detail. When we do the unmixing, there's a system, if you like, automatic way of doing it, which system the spectral analyst swear. So this here is the result from an automatic unmixing algorithm in the shortwave infrared, and there's a similar one for the thermal infrared and for the visible, and they come straight out of the machine. Okay, so being automatic, they're not 100% correct, far from it, and a spectral geologist or someone with a more nuanced view of the geology might edit the spectral library with which we're comparing the spectra and eliminate some minerals, so getting rid of furphies, if you like, and finish up with a user-interpreted TSA or spectral analyst result. So these have had somewhat more processing than the system scalars. And we can go even further and have restricted mineral sets over domains within the drill hole to produce the spectral assistant results and the SWIR and the thermal and the visible. Or we could use another algorithm completely, the constrained least squares algorithm. So there are a number of ways of unmixing available in this the spectral geologist, but the further you move from these S-type results through the U-type results to the D-type results implies the more processing, the more intervention, the more expert input has occurred. Returning to TSG, here's a screen showing individual spectrum where we can bring up a library in purple here, so a library spectrum of muscovite, and compare it with an unknown spectrum in the green. We can see that this, there's plenty of correspondence there, so there's probably muscovite within that spectrum. Maybe it's only muscovite by the looks of it. The scatter screen is our workhorse really in TSG, where we can plot things or plot anything. It's anything here. I'm plotting the wavelength of a spectral feature which is related to the composition of white mica down the drill hole, and we can see that the composition changes so that the wavelength decreases and then increases again. So this might be an anomalous area, and we can see that in this area there's a histogram below showing that this core zone is paragonitic, and it's got zones outside it of muscovite, and then the country rock is pheniditic. So this is a typical standard use of hyperspectral geology and mapping the composition of white mica down the drill hole, typically shown in a scatter screen. The scatter screens can show all sorts of things. We can see spectra, plot anything against anything else. We can have density plots and histograms. We can plot the accentuated color of the drill core here in scatter diagrams. So we can accentuate it in various ways. We can even put false color, like this one here. These two are false color images where we associate red, green, blue with different spectral features. But the top one here is just an accentuated color. So these are, as we go from this browny orangey color to a greeny bluey color, in drill core it may look all pretty much grey, but if you stand there with this log in front of you, you can see that slight variation and get your eye in and then pick it off all the way down the drill core. So it's a great training thing for seeing subtle color variations in drill core, and subtle color variations are mineralogical variations. In a tray screen, we can see not only just an image of the tray, but we can put different measures of, say, mineralogy. So the middle plot here, the color is the mineralogy. And I can see down here where the green bits are, that's where there's a little bit of chlorite perhaps here. And here you can see there's a little color normally associated with that. So we can tailor the screen however you like. And there are partial least squares modeling facilities within the spectral geologist where we can create a model for predicting, say, for in this case, the total sulfides. Here it is from prediction compared with what's measured in a training set with XRD. And the idea is you can build a model here by where you can predict something, in this case, total sulfides, using spectral features using partial least squares or a machine learning algorithm. Okay, we can get pretty good imagery out of the high logger. It's we can see can fill the whole screen. It's supposedly a 0.1 millimeter resolution. It always seems to look better than that to me. And so here's a graph of a small area. We can see image sticks, and you can get this sort of image for the whole length of the core and export it as the whole length of the core as well. We can export tray images. They're all standardized. They have depths and calibration in them. You can accentuate the color if you like. It's all dry core, so but the imagery is pretty nice and it's valued by industry. And we can put all those tray images together to see the whole drill hole, and we could even do that for chips as well. So once you've got results for lots of drill holes, you can start seeing trends and comparisons. Here's a 140 odd drill holes shown on one wall, and if these were laid out in some sort of spatial way, you could use this to map all sorts of geology. Okay, in the second part of this talk, I'd like to use the effect on spectral behavior to show some examples of how we might use hyperspectral geology. So, so there are various things which affect the spectral behavior, like mineralogy and the particle size, and where there's trace minerals in there, and all these things gives us opportunities for interpretation. At the same time, we learn a bit more about what hyperspectral geology is all about. Okay, so we'll go through plenty of examples of this now. In this plot here, we're looking at the thermal infrared area, and we've stacked up spectra for a number of minerals. So quartz at the top, through K feldspar, plagioclase, muscovite, through hornblende, pyroxene, epidote, and garnet. As I reeled off that list, I was really going from felsic type minerals through to mafic type minerals. And we can see in corresponding rocks, felsic rocks through to mafic rocks, we can see that same transition where the general wavelength increases as we go from felsic to mafic. We can kind of model this by either plotting with the location of this point here, which migrates off to longer wavelengths as you go to more mafic rocks, or just the peak, where this peak lies of the general reflectance in the thermal infrared. And if we do that, we can estimate how felsic or mafic the rock is. So here's a scan at Mount Lindsay in Tasmania, plotting this felsic mafic index, and we can see there's the felsic mafic index, and there's the depth. And as we go down the drill hole, there are excursions into different domains of felsic maficness, if you like. It's measuring how felsic or mafic the rock is as we go down the drill hole. So in an alteration system, we could be measuring variations in zonation in the alteration minerals. We could be measuring variation in the protolith. Here's when we look at mineralogy in detail, the silver bullet approach is to find your target feature and see if it's associated with an individual mineral. For instance, here at Canal Bell, gold is specifically associated with occurrences of dolomite in the darker color in here. So, but you know, it needn't be gold. It could be something far more. It could be anything we like. Something that's to do with geomechanics, geometallurgy, alteration, weathering, anything if you like. Gold just happens to be a typical thing that people tend to look for. Here we use the same method. We're looking at a magnesite, potential magnesite deposit. There's magnesite everywhere, but I'm plotting the amount of talc in each of the spectra. And we can see that in a zone like this, in the middle, we have not much talc. Okay, so there's no impurity problems if talc's a problem, which it is. Whereas in the zone just up the hole from that, there's a lot more talc in the sample. So this magnesite would be more difficult to process than the magnesite just below it. So trace mineral mapping can be a great application for hyperspectral geology. Typically, though, we are using the mineralogy to map out zonation in an alteration system. Here's a classic epithermal system with a quartz alunite core and grading out through a zonation or characteristic mineralogy through kaolinite, clays, chlorite epidot as we go to more peripheral parts of the system. So the hyperspectral scanning can fingerprint this zonation. Here's some skarn alteration with showing a zonation from country rock, which is in the black, and more alteration minerals occurring as we go into the core, with the purple being the clay should be pyroxene. Where's our pyroxene? The pinky color. So this is our pyroxene system in the middle of the skarn here, and garnet right in the core, the green color. Okay, so the geologist is making estimates of the relative proportions of the minerals here. The high logger gives a more complete result. So all the areas that were the protolith, which is, as you can see, dominated by plagioclase and brown, are now mapped in, and details of the relationships of the relative proportions in the skarn can be revealed. So the resolution is much greater. In fact, we can go for higher resolution as we like, really, spatial resolution. But we and we have slightly different compositional relationships here. We can see that the garnet here looks like it's been either overestimated by the high logger or underestimated by the geologist. And typically we find that the high logger is more correct than geological logging will do. We can use just the occurrence of mineralogy to find a zonation. Here we have two different types of amphibole leading into granite, carbonates, and axonite into the core of that same drill holes we just saw. So I'm just using the minor mineralogy here to characterize the zonation. But I can do exactly the same thing for pyroxenes and garnet. Garnet will be in the core. So that a range of minerals can be used to highlight where the core of a system is going to be. Here's looking more at a superficial type features. We're looking at opal at Cooper-Pedy, and opal occurs commonly near the base of a weathered zone near the surface. Okay, so here's high logger data. So minerals plotted down a lot of drill holes, and we can see that montmorillonite occurs chiefly near the surface. Gypsum's more widely distributed, in fact, but not right at the surface. Different kaolin minerals are scattered fairly widely, and alunite is concentrated just below the paleo water table. And in fact, that's the interesting horizon. This the zone between at the base of this paleo water horizon is where the opal occurs. So that can be mapped out, and this is a predictor then of where to go and look for opal. In any system where you have surface processes which are of interest, in this case targeting a mineral, but in another deposit it could be that, for instance, copper occurs down here, but also in the weathered area. You really do need to know where the mineralogy changes, and you go from basement rock to supergene alteration, and these are the sorts of plots that will allow you to do that and characterize different parts of the ore, which will have to be treated separately by in geometallurgy. Characterizing this cover can be really important. Here we are in prominent hill, and the geology just shows lots of different types of Cretaceous and younger cover overlying older rocks, which actually have the mineralization in it. The regolith and cover can be characterized just with a few minerals. Here's some high-logger data showing the kaolin abundance here, which is quite variable, and the white mica abundance, again, really variable, and over here the ferric iron abundance, quite variable, which all together allow us to delineate different types of paleo weathering horizons. And this horizon here was difficult to interpret without the high-logger data. But, there's plenty of data here to do that. And so any ore deposit which traverses across any of these zones will need this sort of data to be properly accounted for in geometallurgy. We can use, where we have mineralogy contributing to some other feature of interest, in this case viscosity, we can calibrate it if there's a known relationship between the mineralogy, quartz, kaolin, white mica in this case, and physical property. This can be calibrated so that you can predict the viscosity. Here it's related to the clay content, and we can model this with the hyperspectral data directly. So, so mineralogy, when it begets physical properties, can be used with a high-logger as a predictor. This would have to be calibrated for individual deposits. I doubt if in any case you could apply this over anything further than an individual count. Mineral composition variation is something we use a lot in hyperspectral geology. Here's chlorite, so an iron chlorite and a magnesium chlorite. The major features, the chlorite features here associated with magnesium and iron bonds, vary according to the composition of the chlorite in a linear way. There's a linear relationship between magnesium number and the wavelength of this feature here, but also other features. And we can map that down drill holes. So that's chlorite. We can do white mica as well. Here at Mount Lyell, you can see there's a white mica, the wavelength of a characteristic feature for the OH bond decreases to a core and then increases out here. So in the core we have more paragonitic sodium-bearing white mica, muscovite more peripheral to that, and phengitic white mica in the far field. And these correspond to alunitic and pyrophyllite inner zones, and then more muscovitic outer zones of the alteration. Okay. Absolutely classic use of hyperspectral geology in fingerprinting alteration. Here in northeast Tasmania, I'm plotting the same thing. The orange here is the wavelength of the white mica, and see it takes a little kick inwards to low wavelength as we go across this fault here and here, but it doesn't do that going across other faults. Right, over here a little bit. Okay, so the faults which are mineralized with gold are the ones that have the kick in the white mica composition, but it's only 2 to 4 nanometer difference, which is really small. Okay, so you need, the only way to detect this is to have lots of data, and that's what hyperspectral data will do for you. If you just took a sample with a handheld device every 1 meter, you probably would not have the statistics to be able to pick these kicks. Okay? Now, this data in northeast Tasmania, you'd get exactly the same thing at Bendigo or Ballarat. It's the same system. So very small changes in the spectral wavelengths of features indicating small changes in the composition of the minerals can be exactly what's needed to identify targets, be they, in this case, alteration, but the targets could be trace amounts of clays or something to do with mineralogy. Carbonates, here we have the various carbonates all have individual characteristics in the shortwave infrared to a degree, but in the Thermal infrared, they're miles different. There are three features: 6500, 11300, and now around 14,000 nanometers, which vary markedly from carbonate type to carbonate type. So I'll show an example. Here at Rosebery, you can see that the core of, this is where the ore is, so ore down here corresponds with where we have this purple, which is rhodochrosite, manganese carbonate. There's this halo around that of iron-bearing rhodochrosite in blue, and a halo around that again in red here of kutnohorite. So that's a manganese enriched carbonate as well, but not to the level of rhodochrosite. Elsewhere in the drill hole, we have anchorite and brown or calcite late-stage veins. So the system, we can really pull apart the carbonate mineralogy here. And at Rosebery, this is going to be important not only for targeting, but can be important for processing as well. We want to know what sort of carbonate's there. And of course, characterization of carbonate is going to be really important if we want to look at acid generation effects and possibilities of mixing and dilution for remediation down the line, knowing what carbonates we've got available. So all really useful for processing geometallurgy. Mount Charter up near Helier in Tasmania, there's carbonate in blue all the way down the drill hole, okay, just in little bits and pieces. That's the shortwave at the top and the thermal infrared at the bottom again. It's mostly quartz, but there's a bit of carbonate everywhere. So let's go and pull apart those carbonates. I'm plotting here the wavelength of two of the spectral features of the carbonate, the 6500 in the thermal and the 11300 in the thermal. And we can see we have the carbonates traversing a fair bit of territory here. But if I split these up into different populations, this population here, which is typically where rhodochrosite would plot, we can see that rhodochrosite is characterized by some sort of blotchiness in textures. The calcite tends to reveal itself visibly as nice, sharp white veins, which look late. Anchorite and iron dolomite are these wispy kind of zonations, bandings, laminations within the rock, and dolomite are very sharply bounded microveins, so that the textures of the different carbonates can be seen in the rock and are easily discovered by firstly using hyperspectral data to characterize the populations. So this would be used to get your eye in so that a geologist could then actually see it with their own eyes in the rock. And if we plot the carbonates down the drill hole, we can see most of them are actually calcites in green. But if I throw away all the calcites and look at, if you like, the trace carbonates, we can see a transition from dolomite and anchorite material in this part of the drill hole down to rhodochrosite material further down the hole. So this would be used in a targeting sense. Here's dolomite, not associated with an ore deposit. Dolomite, so Precambrian dolomite in northern Tasmania, and we can see that if we plot a spectral feature, the 11300 wavelength, for instance, as we go down the drill hole, there's variation, and in fact there's two types of carbonate clearly in this larger zone here, a shorter wavelength one and a longer wavelength one. And down here, that looks like there's some sort of trend. And down here, we've got, again, getting two different carbonates with one of the carbonates varying in composition, I guess, because the wavelength's changing as we go along. So looking at all this area in detail, we can see that here's the two populations. So the one with the longer wavelength is calcite. So we have calcite appearing along this side, here, and down the bottom. And this is anchoritic material here, and dolomitic material has the shortest wavelength. So we can see there are zones where we have a transition or a trend from dolomite towards anchorite repeating throughout the sequence. Okay, So this is something to do with, original mineralogy at deposition or diagenesis later on. So we can map all these things out, the composition of the carbonates. Here we are in New Caledonia looking at a calc flysch, so carbonates all down this long drill hole, 2,000 meters long, so lots and lots of carbonate, and we can use it to actually measure the grain size of the rock. So the over here, this plot shows that as the grain size decreases, the spectra are affected in that the intensity of this peak at 6,500 is decreased when you as the grain size becomes smaller, and the wavelength of this feature here, 11,300, increases. So here they are plotted against each other, the strength of that 6,500 feature and the wavelength, the 11,300 feature. So as we go from a short wavelength to long wavelength 11,300, and as the 6,500 feature decreases in size, we go from coarse grain material to fine grain material, which we can plot down the hole. And here we are. These are finding upward sequences revealed spectroscopically. Crystallinity, shortwave infrared is really good for this. We can see here we're plotting poorly ordered kaolinite in the top part of the sequence, and the red here are well-ordered kaolinite, and the well-ordered kaolinite sits below some paleo channel, okay, being picked out here. Here's an example of a similar thing. This is a drill hole in Tasmania, in eastern Tasmania, which has lots of kaolin material in it here, but when we plot a couple of spectral features of kaolin, so the 2200 feature, we plot the full wavelength, the full width of the feature at the half maximum depth, and plot that against the wavelength of that feature. So we're just looking at one spectral feature of the kaolin and seeing what sort of statistics we have. We can see there are two main populations, one down here and one up here, and I can put polygons around those to classify them. Okay, and this middle one here, this is actually dicite, which is the green stuff in the first plot, and we have 4 different types of kaolin, and I can plot those down the drill hole, and you can see that the original data showed it all being basically kaolin. We can now split up into different types of kaolin. Now we don't know exactly what these kaolins are, but they are different varieties, maybe composition, but more likely different types of crystallinity. And in fact, we see the spectra vary. These red ones here have a double feature of well-ordered kaolinite, whereas the blue ones have more disordered kaolinite. So maybe we're mapping the degree of disorder in the kaolinite crystallinity as we go down the drill hole. These can be also used. Here we are trying to characterize aquifers and seals for the purpose of carbon capture and storage. And we can see that if I go to the next slide, that seals we characterize by having smectite and poorly crystalline kaolinite, and aquifers will have more well-ordered kaolinite in them. So an aquifer sitting underneath a seal, which is what these guys are looking for. We can plot water. Here's a spectrum of water by itself, so it's probably sitting in quartz. In this case, I could show it sitting in kaolinite. So a wet kaolinite will have a dry kaolinite spectrum augmented with big water features in it. So we can map that out. Mineral mixtures. When minerals, we see the effects of 2 minerals in a spectrum. Sometimes they mix together linearly, and so we can calibrate that to either measure things like the clay content, or even estimate the aluminium content of rocks which are clay rich. Typically, things are non-linear mixtures. Okay, we've got all sorts of issues. I'll show an example of that. Here's alunite spectrum in blue and a jarosite spectrum in red. When we mix them 50-50 together, we'd expect to see the dotted line, but we don't. We get the green line, which looks more like jarosite at shorter wavelengths and is more like the 50-50 mix in the middle wavelength. So really complicated trying to take a spectrum and work out whether this is what percentage of each mineral it is when you've got effects like this. Here's an example for Arthur River gossans, where we can see that in transitioning from hematite towards goethite, most of the transition from 70% hematite here, or 50-50 hematite, is right down close to the hematite boundary. So most of the variation occurs with just small amounts of goethite in the material. So it's very sensitive to that. It's not very sensitive to changes in hematite when you've got lots of it. Okay, very non-linear. Where to get all this data from? The National Virtual Core Library is online at Ozscope. You can go and search for drill holes, and you can get data from, have a look at the mineralogy. You can download entire data sets. And there are tens of thousands of these, so you can get all that data. So there's a summary of Introduction to Hyperspectral Geology, a little bit about the physics of it, showing plenty of examples where hyperspectral geology is given indications of that have been useful to geologists, mainly in mineral targeting. But in every single case I showed here, I could see applications in geometallurgy. So it just hasn't been used much for geometallurgy. It's that's for you guys. So I hope you see lots of interest in this. I look forward to seeing more geometallurgical applications of hyperspectral geology, and I think you're going to be the people to do that. So you have the ideas, and use spectral geology and find out lots of good things. All right, I hope that was fun. Thank you very much for listening.